Todd Vierra talking about sustainable cities using smart, efficient AI. And I'm here at BrainChip as the VP of Customer Engagements. And what I'm going to start doing is kind of go over why we actually need these sustainable smart cities. So if you look at as AI continues to grow, there's so many new use cases out there causing a lot of bandwidth in the cloud. And we're already seeing AI in automobiles, voice assistants, many other use cases, doorbells. So as this continues to grow, a lot of this AI we're going to see start pushing down to the edge. And these efficiencies at the edge will make these newer cities more cost-effective, eco-friendly, and safer. And the key thing about the edge is you have all this computation that'll have to take some data from the cloud for predictive maintenance, traffic management, and everyday personalization services. We're already starting to see a lot of LLMs and cloud-based computing that'll need to be streamlined. Right now, if you look at like ChatGPT and these larger LLM models, they have huge data, huge parameters, huge memories and uses. If you're going to start seeing this at the edge, you have all these constraints at the edge that'll, such as memory, compute power, and these limited resources are going to be, driving the constraints at the edge that some of these newer applications that run at the far edge next to the sensor will have to be built from the ground up. And then edge AI, will need to become smarter like the brain and take lessons from the human brain, which is the most compute efficient engine in the world. I think right now there are estimates between 5 to 20 watts of power for the human brain. And we're already taking advantage of this with our activation sparsity with event-based computation. And this is how the basis for Akida technology is working. So let me talk a little bit about BrainChip. BrainChip is an IP provider similar to ARM. We license our IP, but because we have this new event-based neuromorphic engine, we have reference designs so we can ensure that everything works correctly, is power optimized, is very efficient with timing and latency. And then we also have our software development environment, MetaTF, which I'll go over in a bit. And we have several customers out there, both on the IP side, and we have many proof of concepts that are evaluating the technology for a lot of use cases. And I'll go over some of those in a little bit as well. And then on top of our customers, we're actually partnering with many of the industry leaders such as ARM, Sci5, Edge Impulse, some of the sensor guys such as Prophecy or Emotion 3D, and then some of the service providers for silicon like Intel Foundry Services and model makers like AI Labs and Texon. So let me talk about data center versus the edge. A lot of times when people talk about the edge, they're talking about the edge of the cloud, where they have unlimited resources, unlimited power, and they're not really worried about model size, parameters, or anything like that. Now, as we start talking about the edge, a lot of people are talking next to the network, which is the network edge. BrainChip actually plays all the way down to the sensor edge where these constraints are extremely tight next to maybe vibration sensors, maybe it's vision sensors, maybe it's a DVS camera, any type of sensor. We work with next to the edge for low power, short latency to have this ultra power efficient design that allows you to work very efficiently at the edge. So right now we're looking at the edge-based designs, and you have to be extremely efficient. And we're about 500x more efficient than the traditional matrix multiplications out there. Whether you're with a CPU, a GPU, or a DSP, all these applications, all these compute engines and AI have to do the true matrix multiplication. Therefore, there's a lot of computation and memory constraints that you can't meet at the edge. And because BrainChip has this Akida technology, which I'm going to go over, it allows you to be extremely efficient. So let me talk about some of the advantages of neuromorphic computation. So it's modeled after the human brain. As I said, it's the most efficient predictive inference engine in the world. And we can run complex models in the neural processor. And one of the interesting things about it, if you're talking about traditional AI matrix multiplication, we actually love sparsity. That sparsity in your design allows for you to do less computation. And I have an example of that in the next slide. So we provide real-time performance, fast and smart computation that allows you to be really efficient. So we make these edge-based trade-offs, and we only process the information that is necessary to compute. So if you multiply a 0 by a 0, that answer is 0. A lot of these matrix multiplication AI engines have to still do that computation. And we actually have a patented technology that allows us to have smart, efficient compute that makes your design very low power and a small thermal footprint. And then because it's neuromorphic, we have unique on-device learning. This on-device learning allows me to add a new classification model that, let's say I have a pick line where I'm doing some classifications of different fruit on an industrial line and looking at apples and oranges and bananas. If I want to add a new class, such as peaches or something, then I don't have to go back to the cloud and retrain my design. I can actually do what we call one-shot learning. And this one-shot learning allows me to take one or a few shots, and I've actually learned a new class embedded in my design by shifting those weights of that new class. There's another application such as device personalization, similar to your iPhone when you first bring it up, or your phone, and it recognizes your face. We can actually have an edge-based layer that allows you to learn different faces for, let's say, an in-cabin automotive design that allows for specific users or drivers to use that car in the environment that it's in without having to retrain on the cloud. And then finally, because we're doing all this on the edge and we're only shifting those weights of that last layer, we minimize that raw data being sent over to the cloud, therefore having a little bit more privacy and security than traditional AI. So let me talk a little bit about how an event-based processor works. So in your traditional AI engine, you actually have a 5x5 matrix, which is your activation map. And what you're going to do is you're going to multiply that by the kernels or the filters. So if I have a 5x5 activation map, and I said what we do is we process things smartly. So instead of doing a matrix multiplication of this 5x5 activation map and this 3x3 filter, all these zeros that get multiplied to get this result, you still have to compute in a traditional GPU, CPU, or DSP. What Akida's event-based processing does, it actually looks for the non-zero values and only computes those non-zero values in the activation map. So therefore, when I do my computation against the kernel, I'm only computing this 1 multiplied by this kernel, the 2 multiplied by this kernel, and the 1 multiplied by this kernel. So effectively reducing my overall computation in this example by 80%. And because activation maps, you don't know where the data is, I'm actually on average reducing my overall computation by 50 to 80% depending on the data set and other things. Now this, what does this do? There's two things that it does. One, it actually, less computation means less power, and less computation also means I get to my result faster. So by getting into the result faster, I reduce my latency. And that is really important on these edge-based designs. So let me show you, it all starts with MetaTF. And from here, I'm going to kind of go into our MetaTF platform, and you can see it's at brainchip.com/developer. And then we also have support module support at brainchip.com/support. So with this, I'm going to exit out of this presentation here and show you MetaTF. So at MetaTF, if you take a look, here's an overview of our framework, our ML framework. And as you can see, we have, this is our SoC that's available that you can get through our brainchip.com environment. And we also have our second generation now available. And I'll talk a little bit about that a little bit later. But you can see there's an overview that gives you a nice update on the framework. It basically shows you, hey, we have a model zoo, how to quantize this information, and goes through some examples and pre-processing. Here's a very important thing in the framework. So you do not need hardware to start with Akida. So we have a software backend, and this software backend will allow you to build your models and run your AI instantiations with a runtime software through our simulator. And I can create a model, I can check for accuracy, I can see how much compute I'm needed. And this is a good way to get started. There's no cost if you just go to the website, brainchip.com/developer, and fill out a form, you get access to it. And then once I build my model, then what I'm going to do is I'm going to get some hardware, and we have these PCI cards available on our products list. And this will allow you to build your model and run it on the actual hardware itself. And once I run it on the hardware, I can get the power and latency from this actual SoC. And because our design is in 28 nanometer TSMC, this will allow you to do some scaling either to higher or lower technologies and get actual numbers based on actual hardware. So you can see, both the software simulator, hardware pass-through, and then if you're a SoC designer, you will actually integrate the runtime engine into your library to build your inferencing environment. So here's an overview. I'm going to click on installation, and here's our supported configurations. Now you can run MetaTF in Windows or Linux. You do need to have Linux in order to run the hardware. And these are the Python and TensorFlow versions, and they can be installed with a quick install command, pip install. Now, if I go over to our BrainChip support page, here's our hardware. This gives you support for the PCI board, PC shuttle, Raspberry Pi. I'm going to click on Get Support. And I'm going to actually, we have some videos on here how to walk through the unboxing, the installation. And I'm actually going to go through our software drivers and show you how it actually install the software drivers. These are very good instructions on how to get the drivers up and running once I get my card. So this will walk you through the different environments. So you can see it just walked through the windows that I just showed you. There's a user's guide in there. So you're going to open your terminal, basically copy and paste into another terminal. And what this will do is this allow you to see, hey, do I have this device? Is it set up? Now, what I need to do after that is go get the drivers from the GitHub, and I'm going to copy these commands. We've tried to make it as easy as possible to get the drivers, the installs, and all the information necessary to get up and running as fast as you can. So now that I've downloaded the drivers, I'm actually gonna run the command to do the install. So I copy it, I paste it into the command window, and now it's installing and building the packages. And then what I'm going to do afterwards is I'm going to copy and paste over to make sure I'm in the right directory. And then I run install. As you can see, everything is installing, fairly straightforward and easy. And we do have a support page that you can email us if you have any questions, if you got these drivers or any issues. So now, after I've installed everything, I'm actually going to download MetaTF and download the Akida engines to install MetaTF onto my board. And as you can see, I'm running Conda Activate. I'm going to have a virtual window that's running. I've actually installed everything successfully. So I got Akida 2.2.1. And then the final thing I'm going to do is actually make sure that the devices are seen. So as I add the Akida devices command, you can see how it now sees the INSOC that is available. And that's the install of MetaTF. Let me go back to my slides. If you have any questions, I'm going to take some questions on the back end of this. So let's talk about the next generation cities of tomorrow. So I don't know how many of you have heard of the line that's out there. And, this is an energy efficient AI city that's being built in Saudi Arabia. And they're doing all kinds of different things, such as driving systems, waste management, public safety. They're having chatbots, virtual assistants everywhere, and traffic management and flow to reduce congestion and improve that transportation efficiency. So let me tell you a little bit about how Akida plays in this environment. So we did talk about the network edge to the sensor edge. So we have several different products where we talk about Akida E. Akida E is the efficient one that stands next to your sensor. So whether you're doing vibration analysis, anomaly detection, maybe it's an always on keyword spotting, sensor fusion, gesture recognition. That's where I need the most efficient, low power, next to the sensor instantiation that I have currently. All the way up to the network edge, where gesture recognition, classification, object detection, or object tracking as well. And then somewhere in the middle, I'm a little bit more balanced, and I could be closer to the sensor edge with these power and timing constraints, or I may need to use more computation, more memory for a vision type application. And that's where the key to S. It plays somewhere in the middle, close to both of these, but I'm actually, starting to do a little bit more sensor fusion. Maybe I'm running more models and more computation or memory is needed. So let's talk about what's going on in traffic management. What we're seeing right now is these smart cities have sensors not only placed in the car, but they're going to have sensors placed around the city. And you can actually see, this is one of our BrainChip demos where we actually run in a traffic management to see cars going through an intersection. But you're also going to see these sensors all around the city as we move forward into the future. So you're not only going to have the autonomous vehicles sending data out, looking for things like people, bikes, and anything that would interrupt your driving experience. But you're going to have that information pass to vehicles as well. We've been working with customers that have these sensors in these, on these street corners to look around where oncoming traffic isn't going to see it, but it'll still send that data to make a safer environment. And with our spatial temporal event-based processor for our next generation 2.0 architecture, You're going to also be able to tell the difference between a person walking across the street and a like a bag or a tumbleweed or something that's not meant to that has a very different movement than a person. So you'll be able to tell the difference between these aspects. So let me talk a little bit about our spatial temporal event-based processor. So we started off with our first generation that actually only had feed-forward networks that we passed through. And as we've kind of progressed and innovated, we've added spatial and temporal. So we have spatial 2D convolutions as well as the temporal 1D. And this allows you to have efficiency where it trains with the back propagation like a CNN, but it actually does inference in a recurrent mode that is highly efficient, but does very nice performance. And you're going to have a lower number of parameters and lower number of memory needed than an LSTMs or a GRU. And this time series data will allow you to be much better and faster than these LSTMs and GRUs. So let me give you some of the results that we're seeing. So if we're looking at an object detection, we've compared a Akida 10s network on CenterNet plus against a ResNet 50 application. And you can see right here, we're getting about the same precision, 57.6 versus 57. And we're doing significantly less number of parameters. So the lower number of parameters, the lower number of operations means my latency is much quicker and my memory is much less. So my model is much smaller. So you're getting a highly efficient, power reduced, low latency model at the edge. And for this video object detection, we can actually model that to see what you're getting in 28 nanometers is 80 milliwatts per inference. So if you go down to 5 or 7 nanometers in your design, it's actually significantly lower than that for inferencing on the edge. So one of the unique features of Akida is we can handle what we call multi-pass operations. So remember that we're trying to run everything without a CPU or GPU. Everything runs within our network. Traditional networks actually run one layer at a time. So you run one layer, it does CPU or GPU compute, and then it has to use the bus bandwidth and the memory access to store those values and then compute another layer. We're actually going to run as many layers as we can in that network. So once we run, let's say the first 10 layers, we're going to try and run everything in one pass. If that doesn't run in one pass, we can actually break it up to run multiple passes through that hardware. And this allows you to automatically and transparent to the user cut up your model so that it runs highly efficient at the edge. And then as I stated before, we have this one-shot learning where that last layer that we put in there, we add in an edge learning layer. And I'll give you an example of how to do that in a couple slides here. But if that last layer, I can either keep my same original classes that I gave you that example with the fruits, and I want to add a new class, or I can have a fully empty last class model for device personalization that if I want to add a family to given a car some usage, so I get into the car, I take one picture of the mom, the dad, the kids, and I can give access to the mom and the dad full functionality of all that car. I could give access to the kids to just the stereo entertainment system. And as I said, we are actually storing these on chip with one shot, only modifying the weights of the new class we just learned. You don't have to go back to the cloud, retrain everything, and go through that whole exercise. It can take weeks or months. So let's talk about some of the use cases some of our partners are doing. We're working with a company called Circle 8 in the Avnet group. And what they're doing is they're building these smart bins. And they're out of Australia, and they're prototyping these right now, where these smart bins will able to read whether it's plastic or glass, separate it, and look at the brands on there. And this will, they're really targeting global waste, because they see that as a crisis. So this is one of the eco-friendly use cases that's out there, and they're starting to roll these out right now. We have another partner of ours that's building models for predictive maintenance. And one of the key things about predictive maintenance, as you're using these AI models in these smart cities of the future, it's going to reduce the downtime, it's going to create a longer life of the product, and it's going to basically increase production of these, industrial applications such as wind farming, or maybe it's energy, energy management. And in AI and manufacturing, you're going to increase the downtime of any supply chain issues or driver monitoring. So there's a lot of ways that you can use AI on the back end to have this smart cities of the future. And then we're also working with another one of our partners called VVDN, and they're building these BrainChip edge-based boxes that'll manufacture these and sell these to the consumers, proof of concepts, and actually they're doing inventory, retail, and branding profiling. So if you're in like a supermarket or a retail store, it's actually looking at what's on the shelf, when does it need replenishing, what brands are being most consumed by consumers. So this will all create these smart cities of the future that is actually happening today. And then one of the other key aspects is audio. So with BrainChip's Akida, we're actually working without Akida right now. You have to bring in your signal. You got some FFTs, and you got a MFCCs that I got to create these MFCCs and then pass the model over to a keyword. And you can see the accuracy is 93% and the memory being used. With Akida, we actually can bypass some of this, reducing the overall cost of your building the system. We get much better accuracy with 7x fewer operations. So fast, efficient compute at the edge is key for these edge-based devices. And you can see we're running at 2 microjoules per inference. And then we're also seeing a lot of our customers doing denoising with these applications. So if you take a look at how they're being deployed, the first thing you're going to do is run a small model at the edge. It does environment detection. Once it determines whether you're inside or outside or next to an airport, then it's going to run a denoising algorithm and then a speech enhancement algorithm. And this approach, avoids expensive data transformation. We've already done training on the Microsoft DSN dataset challenge. You're going to reduce the number of microphones. I think right now in a lot of these environments, there's multiple microphones, and this allows you to have smaller bill of materials cost, real-time scenarios where your system latency for inference must be less than 2 milliseconds. So with that, I want to head back to MetaTF, and let's go back in and show you some more on MetaTF. So as I go into MetaTF, I've already talked about the installation. Okay, within here we have a user's guide. The user's guide basically talks about what are the supported layers in MetaTF. And as I said, we have hardware available in 1.0, but we have the 2.0 simulator available as well. So you can actually do some modeling on our 2nd generation to have some additional features that are being looked at. You can quantize or use our quantized toolkit to go over CNN to SNN. And as I said, we have a user's guide, model zoo. And if I look at some of the commands in the model zoo, this allows me to, build these APIs into my models. And we have a set of examples. And I want to go over one of these examples. The nice thing about this is that we've set it up so easy. So let's go over the MNES example. So you're going to create and train a model, and this is using your traditional AI TensorFlow environment that you're using. I'm going to quantize it and convert it over to an Akida format model. So as you can see, I load and reshape this Avnet data set by doing an import. Then I load it. And this is your first step using your 32-bit model that I'm running. So I'm downloading it from the MSGP. I'm actually running it. There's nothing specific to Akida. This is just bringing it into the environment into MetaTF. And now I'm going to import that model. I'm going to do some rescaling because I have to have rescaling to know kind of how it reflects back from a 32-bit model to an 8 or a 4-bit. So I do some rescaling, and then I'm going to go through the model training. And this is what, here's my commands here, and then this is the output it'll give it. And you can see after I do that, I look at my test accuracy, I get 98. Now I need to quantize it down to 8 bits. So because Akida can handle 8, 2, 4, 1 bits, I'm going to quantize it down to 8 bits, use the quantized model. I'm going to run all these layers, and it does the rescaling again, flattens it. And now I have my rescaled model with a number of parameters. I run compile and evaluate. I look at my test accuracy for 8-bit, and you can see I'm at 98%. So it loses no accuracy at all. And then what I'm going to do is I'm going to run some random samples to check my accuracy after the calibration, and it goes up to 98, about 0.1%. And then the nice thing is now I'm going to, try and retrain it to reduce my number of parameters to 4 bits instead of 8 bits. So now I do some fine tuning, and I've actually ran it through here, and I get those results. I think I'm going to run 10 epochs here. And I take a look at that accuracy, and now I'm at 99%. So now I have a 98.5% model, and I've only quantized it down to 4 bits. So I've reduced my model parameters because remember, at the edge, I want to have the smallest number of parameters that I can. And then I convert it, and now I'm ready to run on hardware. So I've actually ran it, and I've kind of done a test case, and I can see my classification 7 as my 7. So this is a good example of how you actually run through one of the examples. And as I said, we have many examples. There's an AkidaNet, ImageNet, there's a keyword spotting and transfer learning onto how to transfer learn. We got a segmentation, how to build vision models. There's some good examples for 1.0 and 2.0 Akida. And then there's some good examples on how to add edge learning into my last layer and some additional tutorials. And then finally, we have some model zoos. So model zoos for 1.0, this gives you a good starting point. So if I want to train my design on my own data set, this gives you a good starting point to transfer learn on various different models for classification, object detection, facial recognition, keyword spotting, point clouds. And then we also have some 2.0 models that handles a little bit larger array of types of models that you're going to run. And you got AkidaNet, you got transformers, which we now support, object detection, regression, facial recognition, and segmentation. So with that, let me go back to my presentation. And I'm going to show you a couple demos that we actually have running here. So these are demos that people have made for the edge. This is a keyword spotting where we're actually controlling a drone and using it to give voice commands over to the drone. We have the in-cabin where we're actually running 3 models here. We're running a person detection model, a voice detection, and we're adding personalization with the facial recognition. We're doing some vibration sensing that'll allow you to do predictive maintenance or anomaly detection. These are normal working environments where the prediction is on. And, as we, put a anomaly in there, it detects that. And the nice thing about Akida too, doesn't matter what type of sensor. BrainChip can do analysis of any liquid or gas as well. And this is really good for these smart cities of the future, as well as industrial IoT to do vibration analysis for bridges or anything that can built on the infrastructure, and then gesture commands as well. So this is running gesture recognition for gaming or in cabin. If I want to turn lights on, you can actually build a model that does that as well. So let me talk a couple more things. I got a few more slides here, and then we'll go into the Q&A. Want to talk about some of the new things we're doing. We're actually working with time of flight sensors to do anti-spoofing. So you can edge learn. This is a time of flight sensor. So you can actually see depth in here. And this is an image of the same person. So with a time of flight sensor, because I can see depth, you can actually build some anti-spoofing layers so that when you're in cabin and no one can fool the in-cabin sensor with a picture of you. You need that depth to do that. We're also doing health and wellness, so heart rate monitoring and other aspects of health and wellness. And you can see if I'm looking at this heart rate, error rate, which is root mean squared. So we're looking at the state-of-the-art accuracy right here. We're doing 7x fewer parameters and 8x fewer operations. And the key thing is you need to be below a root mean squared of 1 in order to be effective for these types of applications. And we're significantly lower, but we're lowering the number of parameters and operations. So I talked about the time of flight sensor. I'm going to show you the demonstration of this. So you can see how we've actually edge learned the person, but when we put the picture over it, it's unknown person. So as they remove the picture down, it recognizes that it is Rob in this environment. So all these different types of sensors, Akida can actually handle any type of sensor that we work with. It's not about the software doing the work, it's about the hardware doing the work. And then talk about vital signs prediction. This is another model that we've done using the Beth Israel Medical Data Set. You can see with TENS, which are temporal nervous neural network, it's very flexible, not only vision, not only spatial temporal, heart rates, audio, a lot of different things with this temporal event neural networks. 7x fewer parameters, 800x fewer operations. The lower the number of operations, magnitudes lower, gets that efficiency down at the edge, because all these devices at the edge are taking up power and memory, and they need to be reduced to support all the AI that'll be coming out in the future. And then finally, I talked about MetaTF and TensorFlow. At the end of this year, Q4, we will be releasing PyTorch and Onyx support. So you will be able to integrate PyTorch and Onyx through MetaTF, create your model, and really work with our reference chip or any customer's chip that's actually out there from that environment. And then finally, we continue to innovate. we're actually looking at Spike GPT with our edge-based approach and Neuromorphic. Everybody's looking at these GPT models. I think they're on GPT-4 right now, trillions of parameters, but we're actually working with Spike GPT that is highly efficient generative language models. And we're using our event-based activation, and this will allow us to run in recurrent mode and replace these multi-head attentions with our own version of Akida GPT. Continue to innovate, continue to look what's going out there, and really try and optimize for these edge-based inference engines that are really efficient for these smart cities of tomorrow. And as I said, VIT and TENS, acceleration and compression, really important at the edge because you're not going to have as much resources at the data center. So in summary, there's many use cases in the cloud, all these sustainable new cities that are being developed, we're working with effective ways to implement our solutions at the edge. We're working with many companies such as VVDN, AI Labs, Circle 8, and the Avid Group, putting out these proof of concepts that are out there. Our audio solutions are really leading the way for state-of-the-art audio environment for denoising and speech enhancement. And we're at the forefront of providing solutions for the edge-based computations where these constraints are really driving these efficiencies that Akida technology provides. And then finally, we continue to innovate with TENS and generative AI like Spike GPT. And we have the environment with MetaTF, we have the designs, we have the hardware, and people are starting to integrate these into SoCs. And with that, let's look at the questions that we have available.
All right, thanks, Todd. We've got a few questions that came in. I know we're a little bit short on time, but we will have about another 5 minutes for questions before we move on to the next session. One of the questions that came in was, recognizing a new fruit doesn't usually have risk. Recognizing a tumbleweed crossing your car's path may have risk, depending on size or mass. How does your edge algorithm automatically predict risk and generate mitigating behavior without retraining your ML?
Okay, so in our TENS model, if you remember, we're doing 2D spatial convolutions to detect what, let's say what a person is walking across the street. Okay, now that 1D spatial event shows the behavior of people walking across the street. So now I've trained it to know not only what that is walking across the street, but I'm looking at the behaviors. And the behavior of a person walking across the street is much different than a bag or a tumbleweed or any of that. So I'm actually looking at the temporal events in my training pipeline to determine the difference between those aspects of what I'm looking at.
All right. You had mentioned MetaTF. Is there a cost to use that?
Yeah, no, MetaTF, if you go to BrainChip.com/developer, that is absolutely free to start using. We have a lot of examples up there. I showed you in the model zoo and examples. You can start playing with it. Now, the key thing is there's 2 variations out there. There's a 1.0 properties, and then there's a 2.0. We actually have chips and boards available for you to purchase on our product site. So you can go to BrainChip.com, or actually, let me go to my last slide here, or email sales@BrainChip, and you can get access to some of these boards. And once I get access to the boards for 1.0, I can actually start doing analysis. And they have, I think they're about $4.99 on the website, but you can get access to those boards, plug those into any Linux box, and actually get power and latency numbers as well.
Great, thanks. When will BrainChip have support for PyTorch and Onyx, or ONNX, I think? I don't want to say it wrong.
Yeah, that's right. So, I actually run the technical sales team, and we're starting to get some of the internals and testing it out. It should be released at the end of this quarter, early next quarter at the latest.
Great. So I think we've got time for one more question. So let's do this one. In a 1 million volume environment with high value items, people, spaceflight, etc., and using Akida's 98% success rate, what do you recommend using to offset the 2% failure rate? For example, 1 million tests equals 28,000 failures.
So everything is about your training data set. You still go through the normal process of training your data set, right? So I have to have a very good training data set. We're going to get the same accuracy as you do as your normal AI engines would. And that's all about your training data set. So the more and better data I have to train my network using your traditional offline methods, and then basically quantizing that down to 8 4 bits to have a model that will run on the edge, your accuracy will be the same as your 32-bit float. So it's all about the data set and how well that data is to train.
All right, well, that's all the time we have, but thank you so much, Todd, for joining us and giving this presentation. This was great. We definitely appreciate you taking your time.